Well, hello everyone, and welcome back to Adrian's Digital Basement. I hope everyone's been enjoying this whole Macintosh SE30 repair series I've been working on because, yes, we're gonna have another video on repairing SE30s. This is gonna be part 4 in the whole series, so if you haven't seen the first 3 parts, I really recommend you go watch those first. There'll be links down in the description below. Because what we're going to be doing in this video is we're going back in time or back to the future or something like that to work on this motherboard, which was the motherboard from part 1 that I discovered I had accidentally, after recapping it, put 12 volts into data line 31, and that was all due to a little bit of solder resist that was missing right by the capacitor that was near the power connector here. Well, 12 volts on a 5-volt rail going to pretty much all the chips on the motherboard, that's a really bad thing. So in part 1, I did some troubleshooting to figure out that the sound chip had gotten damaged, the CPU was damaged, and the video ROM was damaged. The machine is booting to a state where it sort of crashes immediately when you turn it on, and in part 1, I was very stuck because I didn't really know where to go from there, and it's not my style to just start replacing every single chip on the board until you find the one that's actually broken. On top of that, I don't actually know if this motherboard ever worked properly before I recapped it. And I did this recapping job like a year or 2 ago, and I never really even tested it after that. So we might be dealing with different problems here. We might be dealing with damage that came from the 12 volts, or we're dealing with just pre-existing damage that came from the leaking capacitors, which on these boards has a tendency to eat the traces. So, armed with all this newfound knowledge on how to use a diagnostics ROM and all that kind of stuff, let's get this thing on the bench, plug it into the serial port on my computer here, and see if we can talk to this motherboard to try to get to the bottom of what's going wrong with it. So without further ado, let's get right to it. Rightio, so I'm going to be using my same test setup I've been using the whole time, which is this old dead Mac SE30, or sorry, regular SE power supply, where the power supply was damaged due to a battery leakage, and I've taken parts off of it, and I have a PicoATX powering this thing up with an adapter, and then I have an RGB to HDMI connected up here for the video output, and we can hook this up to the motherboard with the speaker and do some troubleshooting. So as I mentioned in the intro, we're going to be plugging this serial cable into this serial port, the one closest to the jack here. So we'll be trying to talk to this motherboard when we power it up to see if we can find out what's wrong with it. Now, it was in part 2 and then part 3 where I worked on that other motherboard and was able to get really good answers out of the diagnostic mode to figure out exactly what was wrong with that motherboard. And in the case of that motherboard, there were some bad traces. Well, there was one bad trace that kept it from starting up normally. And once I fixed that trace, there was a problem in the video subsystem and due to a bad chip. And then there was also another bad trace that was keeping it from accessing this SCSI stuff. But let's start with the beginning on this motherboard because, well, where we left off when we turned this on, we got a sad Mac tone. Let's see if it's still doing that. Yep, same thing, the slow, sad Mac tone. And as some people mentioned in the comment section, when it's a slow tone, that indicates that the failure is happening, well, early on in the diagnostic phase. And if it's a later failure, you get a faster tone. Now, knowing whether it's later or earlier in the boot phase doesn't really help us though, because it doesn't tell us which diagnostic test is actually failing. It'd be nice if it just beeped maybe different beep codes or something like that, kind of like a flash code on the dead test cartridge for the 64. But for whatever reason, Apple decided that wasn't really worth doing, maybe because it would confuse customers or something, I don't know. And you were supposed to bring your computer into the dealer for plugging into the TechStep, which was Apple's super duper expensive dealer-only diagnostic tool. Well, what we're about to do is access the diagnostic routines via the serial port, which is exactly how the TechStep device from Apple would also talk to this motherboard. And hopefully we can get at the bottom of which test is failing and then start to try to piece together via collecting evidence and whatnot where we have a failure on this board. Now, as a side note, remember I mentioned that the 12 volts on data line 31 went to pretty much all the chips. That goes to all the 8-bit peripheral chips, which are like the SCSI controller and the disk controller and the serial controller over here, plus the sound chip. And it goes to the 32-bit peripherals as well, like one of the RAM sticks, the ROM stick here, that's the ROM sim that is, the math coprocessor, and the processor. This ROM chip here is for the video subsystem. It's on the 8-bit bus, so it was affected as well. So basically every single thing on this motherboard that's on the data bus was given 12 volts, which let's just say is out of spec and really could have damaged those chips. Now, as you can hear, I just reset this machine. It's obviously working to some extent. We can know with certainty right now that the CPU is executing code properly, because it would not be able to make any sounds like that if it weren't for that. And that pretty much tells us the main glue logic chip on here is working properly, the clock generation circuit is working properly, the reset circuit is working properly, and of course the CPU is working because I put a tested one on here along with the ROM sim. And I tested the ROM sim in another machine, so I know that that's good as well. So just as a side note, this is the pattern we're seeing on this machine right now in this crash state. And what this is just the default configuration of the DRAM that's used for the video memory. Until it's initialized by the ROM on this motherboard, this is what you're gonna see. And when it gets initialized, it blanks it out and then draws a checkerboard pattern. You get the mouse pointer and stuff like that. But the fact that we're seeing this right now doesn't really indicate anything other than the fact the ROMs have tried to test this machine and it has stopped or halted the boot process, so it never even gets to that stage. Now, of the two video RAM chips here, this one here that's in a socket that I have a little question mark on, this was on data line 31, so it was also exposed to the 12 volts. And these are 64 kilobyte, 4-bit wide, dual ported RAM chips, and that means they have 4 data bits on them, but they have 2 sets of them. One set faces the CPU, and it got the 12 volts on it, and the other one faces the video display circuitry, which is made up of these PAL chips plus a shift register on the motherboard. It's totally within the realm of possibility that the buffer on data line 31 that faces the CPU and the rest of the system is actually damaged on that chip. And I don't have another one of those chips because they're kind of weird and they're only really used on these machines that I'm aware of. So if I'm able to get into the diagnostic ROM, we can try running some tests against the video RAM to see if that buffer is damaged. And if it is, I'm going to have to take a chip off something else, like maybe one of my other Mac SE30 motherboards, at least until I can go and order some more of those chips off of eBay or whatever. All right, with all that said, it's time to now take a look and see if we can communicate with this motherboard through the diagnostic mode. So I have my spreadsheet up here with the examples and all the different commands and stuff that I've been showing off in part 2 and part 3 and now in part 4. So here's the serial console open, and this stuff you see here was from another motherboard. I just haven't shut the program down since I was working on the last one. Let's see if we can communicate with this motherboard, and the way we would do that is by typing *A to put it in ASCII mode. And if I actually get a response back, then we know that the serial portion of this motherboard is actually working, but if I don't get anything back, then I guess it got damaged. *A, and it is not working, everyone. Oh no! So I think the serial port got damaged on this machine, or there's some other kind of problem here. So *A, yeah. Darn it. And this right here is exactly what I was worried about. I have no idea what components on the motherboard got damaged, and seemingly the serial port did. Just as a sanity check, I'm gonna grab another motherboard and I'm gonna plug this in because I don't wanna go swapping out chips on here in case there's something wrong with my serial connection or the terminal program here. All right, so this is the motherboard from part 2 and part 3, which is now fully operational. So if we turn this on, we're just getting the normal chime, and I'll hit the interrupt button there. And now if we type *A, yeah, okay, we're getting an actual response from this thing. Okay, we're back on the damaged motherboard. There we go, we're getting the slow chime, and we do *A, and yep, nothing at all. All right, well, I think what I'm gonna need to do first, before I do any kind of removal from the board, is we need to take a look at, I think it's this chip here, this is the serial chip. We need to look on the schematics and see how it interfaces, I think, to these little chips here, and see if there's maybe something we can scope on here to see if, well, when I type the characters on there, that it's getting through to the chip here. I vaguely remember when I was doing part 1, I'm not sure I even showed this in the video, but I remember scoping around the chip select lines of the various peripheral chips on here, and I could see that the serial chip was actually being selected by the boot ROM. So it was failing, and I guess what it does is it probably activates the chip, sets up 9600 baud and whatever the default settings are. So it's good that I at least saw a chip select line, but I think we need to go to the schematics and just validate that that's still actually happening, because if we never see the serial chip even getting selected, then it's impossible that it could ever actually work, right? Just like we talked about in the previous videos, you need to have that selection there, otherwise, well, you're never gonna get any communication. So here are the serial ports on the Mac, and I've never had to do, pretty unfamiliar with the way this whole section works. So there are the 2 ports, they go through this resistor pack there. Probably need to start checking to make sure that the receive data is coming through these chips and making its way all the way to the main serial controller chip, which is this 8530 here. But as you can see, this chip on pin 5 is on the data bus, so it could have easily been fried from that little adventure on the 12-volt rail. So the signals come in here through these resistor packs. RX signals, they come into these 175s chips here, and I guess there's some flow control signals. But it looks like the transmit signals, TX, B, and D, where do these go? These go up here to this chip here, 26LS30, and then those signals make their way, well, they go somewhere else onto a different page altogether, but they also go down to this chip. But that's the transmit stuff, right? We just need to start looking at both the transmit and the receive. So for the receive stuff, the assumption is it comes into this chip here, UC12, and then it looks like receive A and B, so that's for the 2 serial ports. So we need to validate here on pins 3 and 5, or rather, if we go all the way to the serial controller chip, here, pins 14, receive A, and receive B on 31. We need to validate that we're actually seeing stuff there when I type characters on the keyboard, just to make sure that it's actually getting through. And maybe it is getting through, and maybe there's a break in a trace or something for the transmit side. So maybe when I type like *5, we might start to see something on the transmit line here if there's a broken trace. But we also need to check this, which is the chip select line and the read and the write signals, because just like the SCSI controller in part 3, you need all 3 of those signals working in order to have the serial chip even do anything at all. So let's actually start there with those 3 pins, and then we'll start looking at the transmit and receive lines. Okay, let's start with pin 40 here. So this is the right pin. Didn't really see anything there, did we? So if we go to normal trigger mode and I hit the reset button, if it triggers at all. Okay, oh, there we go. I was gonna say, I didn't see anything, but it did write to the chip. All right, so we know the right pin is working. Let's go through the other ones. All right, I am going to look at pin 41 now. Oh, which has constant reads. Okay, so it means it's pulling for key presses. And now we're on pin 38 and there's plenty of chip selecting going on. So that means these 3 signals are making it through to the chip. So that is not the problem. It's definitely being selected and it's definitely trying to pull the chip and trying to read it. Let's go investigate these read and write lines now. Okay, so here's the receive pin. Let's type on the keyboard here. Yep, there we go. I'm just typing on the terminal right there and I'm actually on the serial chip itself. So we know that the RXA pin is used for the diagnostic mode, and it's just, this chip is obviously no longer able to communicate on the bus anymore. And probably it's just damaged internally, or the data line 31 buffer that's on there is bad.
Did you just catch my error? Unfortunately, I made an assumption that just because I was getting RX signals into the chip, that the chip was bad because we weren't seeing any output on the serial console. But what did I forget to do? I didn't actually look at the output signal to see if I type commands if we actually had any output. I just right away assumed the chip is bad because we weren't seeing anything on my terminal emulator. I basically violated one of my critical rules that you have to gather all the evidence you can just to make sure you don't do unnecessary work.
Well, that means I'm gonna have to do another PLCC soldering job, which is not something I like to do. But people did have some suggestions that really the only real way to do it is to use hot air. And ideally what you need to do is sort of like cover up the stuff around it, you know, with some aluminum foil or whatever, blast this with hot air, get the chip off, clean the pads really well, then lay down a very thin bead of solder paste, which I think I have some up in the fridge upstairs. And then you put the new chip in place and use hot air to reattach it. And that's the way to do it. I was trying to use my soldering iron and it was just pain, especially when you have stuff like this in the way. So first we need to see if this Mac2CX is gonna be a good donor for the serial port chips. Is this it right here? Yep, that's it right there, 8530. So that's good, it's far away from any kind of damage, because if it's anything over here, this chip is looking massively crusty there. Oh, that poor ADB chip. But luckily we can rule out that it's not these little chips, because you can see that one's got a bunch of cap leakage damage there. So yep, this one over here, which is in good shape, that is what we need to work on.
So based on feedback I got from comments on the previous video, I decided to use my big heat gun to preheat the board just to aid in removal of the chips and for reinstallation. So here I'm just sort of touching to make sure the board's not too hot, but I'm really heating it up. And now I'm using targeted hot air at around 350 degrees around the chip, so it comes off the board. And it came off relatively easily, and the preheating definitely made a big difference. For removal of the chip from the SE30 motherboard, I used preheating on the underside of the board first, and then I put tin foil or aluminum foil all around the chip itself, and I'm using hot air to remove it. Sorry for the bad camera angle, you really can't see what I'm doing, but I'm just basically doing the exact same thing I did on the Mac 2CX motherboard. Now it's just a matter of cleaning up the pads, and I'm using a little piece of solder wick here and using some tweezers to move it around, just keeps my fingers from getting burned, and I think this did a pretty good job at cleaning up everything. The wick does leave a lot of flux behind, so a little IPA and a bit of scrubbing just gets everything all nice and cleaned up. Now I'm going to apply some solder paste onto the pads, and I have absolutely no idea how much to apply here. I've never used this solder paste ever in my life. So here we go. I'm just kind of guessing and running a very, very thin bead of it across all the pads. And finally, after preheating the bottom of the board again, I'm using hot air, well, targeted hot air, to try to reattach the chip. Again, I don't really know what I'm doing here, so I'm just trying this out. And yeah, holding down the chip once the solder had seemingly melted, I'm just applying a little more targeted heat just to finish it up.
The chip's attached. I think we have some bridge connections. I don't think that worked exactly as well as I thought it would. People said in the comments that it would like, whoop, it would like pull itself on, but it definitely didn't seem to do that. Now, I don't know if that was due to the paste I was using or I didn't use enough or whatever. It's this MG chemical stuff, but there's obviously quite a lot of technique to doing this type of work. And as I mentioned in my last video, when you do these little surface mount chips, these SOIC, I think they're called, these are so easy. I can get those on and off boards very quick and easy. But these PLCC ones, not quite so much. Now I was thinking when I was putting this on the board that I bet you the reason why the sound chip and this were damaged is I bet you the computer was crashing and the glue logic or the glue chip was selecting the serial chip for the diagnostic mode and the sound chip. And of course, as soon as it turns on its buffers, well, that might have caused an issue there. Yep, you can see there we got some shorts and they're underneath the chip. Oh, the worst place to try to get them off. How about over on this side? That side might be okay. There's one there, it looks like. All right, I think I'm gonna cut the camera and I'm gonna try to sort this out. This is what makes it so frustrating to get these on and off. Okay, clearing the shorts off those few pins was much easier than I thought it was gonna be. I think I'm just getting better now that I've done, how many of these chips? This will be the third one I've installed onto this board. Also, I think the method of using the solder paste and hot air was definitely a lot easier than getting these two onto the board. So that's the way I'm gonna do any more of these that are bad. And if I have to do this chip, man, that's gonna be hard because the bigger it is, the more difficult it is. But let's see what this thing does. Let me just clear off all the things it can short off of. Let's see what this thing does now, at least with the serial port. I'm sure we still have a fault on this board. I doubt it was failing simply because of the serial port. Okay, so no change there. Let's get the serial port cable plugged in here. And let's turn this back on. And do we have a functional serial port? Oh, we do not. Ew, boy, oh boy. Okay, what I'm gonna do is just double check that we still have the select lines, and the one you see right there is the right pin. So that's as it sets up the serial port. And this is the read pin. And I'm touching to the top of the pin that's on the body of the chip just to make sure I don't have like a bad contact or something. So that's fine. And then this is pin, I think 38, chip select. So that looks good as well. So I'm curious, while we're looking at chip select, what happens if I type on the keyboard here? Oh, very interesting. Did you see that? There was something that actually happened there. *5. Huh. Why did that change so dramatically? Let's reset this. You know, I never checked to see actually if the signal was getting out of the serial chip, like if it's transmitting, because if I type *5, well, star A, and then *5, it changes like that. And *5 should be printing this message right here. And it's absolutely doing something different now. Interesting. Let's check the transmit pin. So the transmit pin, we're talking about the A ports, right? Because we looked at the RXA, it's pin 16. Okay, so I'm on pin 16. Hey, it's freaking doing something. I never looked at this pin. I didn't really check to see before we took that chip off, and I guess that was my bad. That chip could have been working the whole time. I just assumed because we were getting receive signals that we... Oh boy. Okay, well, that's the output pin, and we definitely could see it doing stuff there. So there's obviously a problem where it's not getting to the serial connection here. I'm just gonna restart the serial console. I mean, we know it works because we saw it working hooked up to the other Mac, right? But just in case, we'll change this to the correct parameters here. We'll put that there. We'll turn this on. I don't have a speaker hooked up, so you didn't hear the bong, but I'm sure it has just crashed *A, and there's nothing. So what I'm gonna do is I just wanna 100% validate that it's receiving our commands. I'm gonna try to do a memory test of the video memory, and the one that's actually working is this extra RAM test. So if we just paste this into here, whoa, it actually did the test. So that actually implies that it is responding. And I'm confused. Okay, well, first of all, we're getting the lines because I think data line 31 on this RAM chip is damaged. So that's not working. And that's why we're getting that white line. This should be a full black screen. And I'm back in the serial console. If I paste the RAM test command again, it should flash. There we go. Yeah. So it absolutely is responding to the serial communication. Now what I'm gonna do is I'm gonna try to see if the RAM is working, because I'm gonna paste the little assembly language program in that's gonna fill the entire screen with white. And what it does is it loads it into the RAM and then it tries to execute the code. Let's see if that's working. So if the screen changes to white, okay, clearly we got some issues going on here. Let's try changing it to black. Let's see if this actually is responding. Yep, okay, so it hasn't crashed or anything. The video memory is definitely messed up. And now I'm gonna do the program, the little assembly language program that causes the animating line to go across the screen. And let's see if this works. Here we go. There it is. So we definitely have a problem with the video memory, without a doubt. So it's this chip right here. I'm gonna have to get another one of those chips. But what we do know for sure right now is that the CPU is executing the code that's doing this animation out of the main memory on this motherboard. We know that serial port's working enough for me to send commands to it. I just can't see any responses back for whatever reason. But I've clearly got ahead of myself because the video RAM problem that's something else we need to deal with. First, we need to figure out why I can't get the serial port to work properly. Well, I mean, it's obviously receiving what I type. Why isn't it transmitting back properly? And then we have to solve why this machine is crashing and what diagnostic mode it's failing. And then we can move on to try to fix the video memory, which I think is just going to be replacing that chip. So let's go to the resistor network here. So the transmit lines come in on pins 13, 14, come out on 8 and 7. Okay, so I'm on the input to the resistor network. I think it's like pin 13, and there's the signal, and it is refreshing. And now I'm on pin 14, which should be the opposite signal. Let's switch this to auto, and there's nothing. I mean, there's a little bit of something on there, but definitely doesn't look like what I would expect it to be. Yeah, 13 and 14, TXDA plus, TXDA minus. So differential signaling means that one signal will be inverted from the other. And I think this is used for the AppleTalk protocol, but obviously RS-232 is not using it, and it's only going to be using one of those two signals. And I'm thinking it might be using the positive signal, which doesn't seem to be getting through to the resistor network. So TXDA plus, that is coming from pin 19 on the little, whatever, this buffer driver chip here, which I am on pin 19 here. And there it is. There's that serial signal. I don't know why it's triggering like this. Oh, I have it on auto. That's why we switched to normal. It will only trigger when the signal is actually sent. Okay, so we see it sending the data, and there's the opposite signal, which I'm on pin 18, and it is working. So there's our problem. TXDA plus pin 19 is not getting through to pin 14 on the resistor network. That means we have a broken trace. Was this the problem from the very beginning? Unfortunately, the testing I did before I took the original chip off wasn't sufficient here. I checked those chip select lines. I think I checked to see that the receive signal was coming in, but I actually never really looked to see if the transmit signal was coming out. I guess it's too late now. I've already swapped the chip, so yeah, here we are. So the signal goes missing between this chip and this resistor pack, and then it makes its way to the serial port. And look what's right here, capacitors. They obviously leaked all over the board, and I didn't really look to see if there were bad traces or not there. And I guess I really need to do that. Well, you know what? I see a bad trace right here already. I don't know if that's clear in the camera, but it looks like something coming from this chip is already bad. So once again, I'm just gonna do a bodge on the top side. Okay, so to the best of my understanding, this pin, which I think is 13 on there, goes to pin 19. And then that pin there goes to this pin. And that's what's broken, right there. So I need to put a bodge wire from that pin on this little mini PLC chip over to there. And that should fix this problem. All right, so the bodge is installed. Let's just make sure that, obviously that's connected now. And this other one here should be connected over here. And it is. This is the receive line, and this is the transmit line. Now, when I installed this, especially over here on this chip, I did smell a little bit of that fish smell. So I thought I cleaned this board when I pulled the caps off, but maybe I didn't. There's definitely some dirt and stuff on here. So I guess I didn't really wash these boards very well after I did that. So hence the fish smell. But what's really obvious here after working on these boards now is that the trace damage from the leaking caps is absolutely insidious. And even though the pads and where the capacitors were when I removed them, they weren't really that crusty, and the board didn't seem like it was particularly damaged, clearly, well, this thing has at least one bad trace. We might have more that we're going to be finding. And now I'm starting to suspect that this board's not working specifically because of these traces that are damaged and not because of the 12 volts that I put into the board.
Oh, how wrong I am.
We obviously know for sure that the CPU was damaged, the sound chip was damaged, and the video ROM. But what I don't know is I switched out VIA1 and now I've switched out the serial chip, and I don't actually know for sure if either of those chips were actually bad. Luckily, the VIA is just a 6522 and the serial chip is also like an off-the-shelf part. They are not custom Apple chips, like the sound chip, which was damaged. Okay, we're ready to see some diagnostics running on this thing. Let's turn it on. Okay, we knew that was gonna happen. That definitely wasn't gonna be fixed from putting that bodge wire in. Star A. There we go. We are now in diagnostics mode. So star 5, that's what I was doing to get that Apple banner. And there's the failure. And it is a 5. Heading over to the spreadsheet to take a look at what 5 is. RAM addressing. Interesting. I'm thinking we have a bad trace again. And that's because the glue chip, which is what handles all the RAM addressing, well, that's not even on the data line. So I don't think it would have been damaged necessarily. Let's run through some of the diagnostic tests here and see if we can gather more information. Star 4 to reset the response code, and I'm going to paste in the test for the RAM size. And this machine has 8 megs of RAM installed in it right now. So if we do star R, it's only seeing 1 megabyte. It's kind of similar to the other one. So when you do the RAM sizing, essentially what you're looking at is this digit right here is the size in megabytes, and it's hexadecimal. So obviously if you have 8 megabytes, that should be an 8. And when you have 32 megabytes, you're gonna have a 20 right here. So it'll be 2 and 0. And 20 hex, as you can see here, is 32 in decimal. Well, for fun, let's do a data bus test here, which I'm assuming is gonna pass. And it does, we're getting all 0. So data bus is working fine. And if you recall, on the last motherboard that I fixed, it was getting a data bus error as its failure when you first powered it up. So the sad Mac tone, playing slowly, is the same with both this addressing problem and the other machine with the data bus problem. Now we have a test here called address line test, which I've never actually tried. Let's see what happens when we run this. we're getting zeros. But what's not exactly clear to me is, do we need to set a start and end address? Maybe. So why don't we grab these two for 1 megabyte of RAM, and we'll paste this in, and we'll do this address line test again. It finishes really quickly, so I don't think that actually matters. It doesn't actually use those parameters. Okay, well that's weirdly enough is working okay. We can do a ROM checksum as well and see what this responds with. Just all zeros, so I guess that means it tests okay. Now let's run this extra RAM test, which I know is actually testing the RAM. So we'll paste that in. This is only going to test 64K. I keep doing the lowercase r there accidentally. So the 64K of RAM is testing correctly. And what I'm going to do is I'm going to copy in the value for 1 meg of RAM here. And let's run the extra RAM test here again. Oops, I think I ran it twice accidentally. Aha. Right, so we're getting bad bits here when we're testing the entire 1 megabyte of RAM. Now, when you have 8 Fs like that, it's actually telling us that all of the bits are testing bad. But we tested the 64K of RAM a moment ago, right here with these two values, and it actually worked fine. So I'm wondering if we're missing an address line here, and that's creating some kind of a page error. I'm gonna set it back to 1 megabyte of RAM again. And I'm going to run the mod 3 RAM test. All it's going to do is fill up the memory with a pattern that repeats itself. And we can see that pattern if I copy this read value from memory here. We hit OK. There is part of the value, but let's change this number here from 4 to like 400. And you'll see that this will read out a lot more data, and it will just, there it is. Oh, it goes pretty quick too. But I'm going to say this actually looks like a problem, because I recall running this test on another machine, and the pattern seemed to be a bit more of a repeating pattern. And see how all these bytes look the same and there's zeros in there? I don't think that's what it normally does. Now look at my notes for test number 2, which is the one that filled up the RAM there. I observed that before it wrote these patterns here, these 3 repeating sets of bytes, DB, and then 6D, and then B6, over and over and over again. I really don't remember it writing these repeating patterns here, where it's the same over and over again, and then anything with a 0. I guess we can confirm this by just hooking up one of the other motherboards and giving this test a try. I suspect there's some kind of an addressing error happening, and probably page errors are happening, where essentially if you write to one location of memory, it overwrites another location, and that's creating that sort of pattern that doesn't look correct. Well, as you can see there, as I scroll back, and I am scrolling back right now, and it's hard to tell because the pattern repeats, there are no zeros, there are no like bytes that are repeated like we were seeing on the other machine. So my notes were correct, that the pattern you should see when you fill it, the RAM up with that RAM test is just these 3 sets of repeating bytes over and over again. And now I just have to decipher what that means exactly and what kind of an error could possibly be causing that fault. All right, so we're back on the damaged motherboard here, and we'll just repeat our test here. So first I'm going to dump the memory without even filling it, just so we can see what it looks like. Wait, what? Why is this pattern in here? This is definitely the damaged motherboard, but it has in here what looks like the RAM test that we just ran on the other computer. That's very, very confusing. So the question is, I haven't even run the test to fill the memory yet, and why are we seeing that pattern? And we're not seeing the pattern with all the zeros and stuff. Is it possible that the Mac actually just ran this RAM test on the entire memory? I'm actually thinking that's probably the case, and we're only looking at the first 400 bytes. And I think the memory test that happens when you first turn on the computer is really only the first little section of memory. It doesn't test all the RAM right away, at least. And maybe when I specify that we have 1 meg of RAM and then I test it all, that's where the addressing errors are coming in. But when you do a small RAM test of just a small part of memory, like say the first 64K, it tests just fine. Let's just confirm that ourselves. Okay, so first we'll start with 64K, then we'll run the test, and now we're gonna look at the first 400 bytes. That looks totally fine. No issues whatsoever, right? We're seeing a really good pattern. But now if we run this entire test against 1 megabyte of memory, which is gonna happen right here, Now, when we take a look at what's stored in memory, yeah, we're seeing weird patterns again. Look, the zeros are in there, and there are those repeating bytes again. So it definitely feels like there's page errors going on. And what I mean by that is as the diagnostic test fills up all the RAM with this pattern, as it gets to higher up addresses, some of the lower addresses start to become affected and not work correctly. Now, in looking at the memory that's on the board, I actually realized these are 256K SIMs. So these SIMs here are only 1 megabyte, the first 4. And then I think the second bank that's on here is also only another 1 megabyte. So this only has 2 megs of RAM on here. Actually, you know what I'm going to do is I'm going to take the memory off the other motherboard. I'm going to use known good memory on here just to kind of rule out any potential issues with this RAM, because maybe we're dealing with actual RAM issue here. Honestly, every time I take the RAM out of these SIM sockets, I feel like I'm going to break something. It's like only a matter of time. I mean, luckily I have replacement sockets, I guess, but still, I don't really feel like having to go and fix this. Okay, I have 4 megs of RAM in here that was on the other motherboard. Let's turn this on. Maybe this will suddenly fix the issue. I don't think so, but maybe. No, okay. It did not fix the issue. Okay, so checking the response code now, we're getting a 4 and we're getting a 5 here. So the same error code, we're getting like a RAM address error, but this was a 1 before, and now it's a 4, which is oddly similar, I'm thinking, to the RAM size. Let's clear out the response code. Let's run the RAM test and do response code. Hey, it sees it's 4 megabytes now. Okay, well, anyways, let's do the same thing with the RAM test, except I need to do it over the entire 4 megs now. I might as well add another one of these for 4 megabytes. We'll just put it down here. We'll run this mod 3 to fill up the memory. It's going to take a little bit of time before you even get a response, but it is working. It should be working. There it is. There's the T. And we'll read these 400 bytes from memory again. Yep, and it's screwed up in a different way. Like, we're still getting the zeros here, and we're getting these repeating bytes, but you notice the pattern looks a little bit different. All right, well, with the evidence we see here, it definitely looks like we're still having a page error. But as to why it's happening, I'm not 100% sure. But I guess what we need to at least do is take a look at the SIM sockets here and check all the address lines. Okay, so I'm on RAAF0 here, and if we hit the reset button, no real change. It kind of goes away for a split second when I hit the reset button. Well, all those address lines and the data lines look totally fine. Now, there's a capacitor down here on the bottom of the board that could have affected this lower SIM socket, but I don't think that's the problem. Like, if the address line was, say, broken on this lower SIM socket, but it was okay on these, I think if we did the RAM test, it wouldn't show bad bytes in all of the memory module. It would just show it in the lower 8 bits that this SIM is on. And these ones would be fine, because this is the lowest bits, 0 to 7, and that one is the top from 24 to 31. So now that has me thinking maybe there's something with the glue happening. And I'm not going to jump to the conclusion that the chip itself is bad, but maybe one of these address lines going into it is somehow bad, and maybe I don't know. If that's the case, though, I don't see how the ROM would even work, because obviously the ROM is being selected by the glue chip. And yeah, there it is. There's the ROM select line. Now, if one of the lower address lines were somehow bad, it could possibly cause it to work where the ROMs weren't working, but other things weren't. The sound is working as well, so we have I/O that works, plus the serial ports. Ah, wow. It probably makes sense for me to kind of focus in on this top part of the glue logic chip, because that obviously is close to those caps. So if there's any kind of address lines in this area, maybe there's a broken trace going to those. So I think I need to take a look at the signals on the top side of this chip and see if there's address lines there. Okay, so those pins are 54 to 74. So there's definitely address lines in that part of the chip there. All on this side here, there's a few address lines. So let's start on pin 55. I don't know where 54 is. Maybe it's used for ground or 5 volts or something, because it's not here on the schematic. It's obviously going to be hooked up to something, right? Do we see the 5 volt lines on here? I don't even see them. So yeah, it must be a ground or power pin. and it's just missing from the schematic. So what we're going to be looking for is activity to show up here on the oscilloscope screen here. Well, I'm at a loss right here. I can't find anything out of the ordinary. All of these signals going into the top side of the glue chip that are closest to the caps are fine. I don't notice anything out of the ordinary, and all the address lines, there aren't that many. They all look good. The one thing I am curious about here, though, is there are two signals that go into the top side of the glue chip, RAM size 0 and 1, and they make their way to the via number 2. What exactly do those signals do? They just go to page 3. I should look at these, the outputs here from via 2, and see if they do anything at all, and then compare that to the working motherboard. So let me grab the other motherboard again and compare these signals, see what they look like. All right, so on the working motherboard, when I hit reset, we get a pulse. But yeah, we're getting pulses there on both of the RAM size outputs. And now we're back on the broken motherboard, and when I hit reset, okay, yeah, we're getting the same pulses. You know what, actually? Okay, so this is pin 8 on the via, and the RAM size pins are 8 and 9. And now I'm on pin 9. Pin 9 is just always high. But back on pin 8, we get the pulse there. Curious, very curious. Now here's the thing, take a look at the 8 bits of output on this via. Could it be that data line 31 is damaged and therefore it can never set that particular bit because probably it accesses a register or whatever to set up all these bits all at once, and that one never gets set? Maybe. Pin 8 here, RAM size 0, might correlate to data line 30, but data line 31 might actually be the RAM size 1. I'm just going to go back to the other motherboard real quick just to double check that pin 9 there was pulsing. And yep, there we are on pin 9, and without a doubt, every time I hit reset, it pulses. What also, unfortunately, is not clear from when you look at the schematics here is you can't really tell if these are configured as inputs or outputs. They can work either way. And I guess it's theoretically possible that the glue chip is generating those two RAM size signals and sending them to the via, but that doesn't really make sense. I'd really think that it has to come from the via, like it's something the ROM sets that maybe configures the amount of RAM or something in the glue chip. I don't know, because the glue chip might have been designed originally with like jumpers in mind, so when it initializes, it needs those signals to be set a specific way. It's just very suspicious to me that it's this PA7 that's not working when, of course, it's data line 7 going into the chip, which is the one that got 12 volts, and that could be the one that's potentially damaged. And via 1, which is up here, I already swapped that one out. Yeah, it's just really hard to know what to do next because there's nothing super obviously wrong right now with the whole RAM subsystem. And yet, it's clearly not detecting the amount of RAM correctly, and then we're getting these weird addressing issues. And I'm wondering if it's just the lack of that signal pulsing low when the system first initializes. So armed with questions about how this whole RAM size thing works, I went to our local Portland Retro meetup group on Friday, and I was chatting with one of the other members, Super SVGA, and asking about this particular issue. Well, later that night, Super SVGA sent me a PDF of this book here called The Guide to Macintosh Family Hardware. And in it is information about exactly how this whole RAM size thing works. And those two pins on VIA2 are output pins. The two RAM size bits are set up at system startup by firmware, so that's the ROM code, to indicate the size of the RAM ICs being used in the RAM sims in Bank A. Table 410 shows how the bits reflect the size of the Bank A RAM ICs. The RAM size bits determine the physical address at which the glue IC stops selecting Bank A and starts selecting Bank B. And if we take a look at table 410, we can see that when the bits are both low, that means 256 kilobit memory modules. But what we saw on the oscilloscope was that V2 RAM 1, that's this bit right here, was always stuck at 1. And that indicates 4 megabit chips, which is 4 megabyte sims. And that's definitely not what I had installed. Now, the thing is, when I was doing that testing, I don't think I even had all the memory in the machine. I think I was missing these 2 lower modules. So what we should do is put these same 4 modules, these are 256 kilobit modules here, into this motherboard. We'll just check the output of VIA2, and then we'll put these same exact modules, this 1 meg of RAM here, into the other motherboard, and just double check, just to validate that the signals do look different between the 2 systems. Okay, I'm on pin 8, which is the one that should be working, and I hit the reset button, and it pulses low. In fact, when I hit reset, it goes low, and then I let go, and there's the pulse. And now I'm on pin 9, which is the one I suspect is damaged on this chip, and if we push auto, we can see here that it's just stuck up at 5 volts. All right, let me switch to the other motherboard. All right, so this is the working motherboard. It has 1 meg of RAM as well, so 256 kilobit RAM chips. We turn it on, and I'm on pin 8 right now. And actually interesting is that signal pulses, but I notice once the system is actually running, that signal just goes low and stays low. But that might be because this system is actually booting. And if I reboot it and hit the interrupt pin, yeah, it doesn't actually stay low. So reboot, pulse, and I hit interrupt, and I think now it just stays high. Oh, no, it's staying low actually. Well, anyways, now I'm on pin 9, and we hit reset. It goes high, and then goes low. And if we go to normal, do we see that same pulse? It's interesting, so it pulses, and then it actually just goes low and stays low, which is what we see here when we do normal. Now, what's really exciting here is this is actually the first lead I have as to what might be wrong with this damaged motherboard. And my hypothesis is VIA2 is damaged, and it's not being set correctly to indicate the RAM size. And I think what that means is the glue chip, which is the main PLA type chip on the motherboard, is being tricked into thinking that this has a different size of memory than is actually installed. And therefore, when you go to write to the memory, very strange things start happening. Now, one thing I can try before I remove this chip and swap it out is that this bit is always stuck at 1. Well, 1 and a 0 indicates 4 megabit chips, and I happen to have 4 megabit chips. So let's put 16 megs of RAM on this thing, and maybe suddenly it'll start working. I don't know. It's worth a try. So these here are tested 4 megabyte modules. So let's pop these into here. And again, I really hate installing memory onto these sockets. Oddly enough, the other motherboard with the white sockets, they seem to be a lot easier to use. Like, they don't feel like they're always just about to snap compared to these ones here. All right, let's turn this on and see what happens. It freaking just gave a good chime. It gave a good chime, everyone. Did you hear that? Oh, that was it. That was freaking it. Now, we, of course, are dealing with the bad video memory still, so this chip right here is bad. But, I mean, we have a mouse pointer and everything. So, plug a mouse in there. ADB does not seem to be working. Oh, dear, oh, dear. Now, it might not be working because ADB is communicated with through the vias, and maybe it's through via 2, which we think is damaged, right? Let's hit the reset button here again. So the mouse pointer appears, but not getting any mouse activity. We're also not getting the flashing question mark, which could indicate that the SCSI chip is bad as well. So it's kind of like, I think a lot of people suspected in the original video where I first showed this motherboard that basically everything on the data bus was going to be damaged, and I think that might be the case now. So back on the schematics, via 1 is actually what communicates to the ADB, not via 2, and I already swapped via 1. I don't know for sure if via 1 is actually working. Let's just see what else is on via 2 though. So we have the IRQ, that has to do with the expansion bus. I mean, it would normally be the new bus slots, but since this has PDS, these IRQ signals come from the PDS slot. We got the RAM size there. And I don't think this stuff here has anything to do with the Apple desktop bus. It really is all coming from this chip over here. Now, in case you think the ADB chips themselves might have got damaged, these are the ADB ports right there. And the ADB chip itself and the real-time clock, they both do not sit on the data bus. So those two chips wouldn't have been damaged. And unfortunately, as you can see, the machine just sitting here, we don't know if it's actually frozen right now. I'm gonna hit the non-maskable interrupt, see if I can cause it to crash with a SAD Mac. Yeah, okay, so we got a fast SAD Mac and we got 13 there. Well, okay, I think we kind of know what needs to happen now. I'm gonna need to swap out VIA 2. I also need to swap out the video RAM chip because we clearly know that's bad. Now, I was looking through my spares trying to see if I had anything that would work in this position, and I don't have an exact replacement. But what I did find is this board right here, which is some kind of like old NuBus card. It was already missing some chips, but I've also harvested some things off of this. It was a monochrome display port adapter. You can see there's only one connector there for the video. Anyhow, it has some video RAM on it. Now it's in this zip configuration, and the part number on here, it's a Hitachi 53451ZP-10. And a quick search of that part number, take a look at this. VRAM 64K times 4. And looking at the data sheet, it says it's a multi-port CMOS video RAM chip. My assumption is this is completely compatible with the part that's on there. We're just gonna have to double check the pinout of it, but it looks like, yep, it's definitely dual ported. So we have IO lines there, we have IO lines there, and then we have the address lines down here. So I think this is gonna totally work. And I'll just need to make an adapter that goes from the zip form factor here into the normal dip size. And I happen to have a data sheet for the NEC part that's actually used on this board. And there it is. Yeah, it's exactly the same. And in fact, the NEC one also comes in a zip package as well. But one issue is that the zip form factor has quite a different pinout. And that's kind of frustrating. I was hoping I could get away by like plugging half of the zip chip into one side of the socket and then just wiring up the other side. But I'm gonna have to make an entire little adapter board with a bunch of bodge wires to even make this work at all. But the good thing is it will be possible. It's just gonna be kind of annoying to do. I took a look on eBay at the price of the NEC chips that are on the board, and they're like 10 bucks for one. And these are untested, like old parts, so who knows if they're even good or not. So I think $10 is worth my time just to kind of see if I can make one of these zip packages work, since I have a bunch more on that old video card anyways. Okay, so I think what I'm gonna do now is I'm gonna remove VIA 2, definitely seems to be damaged. I'm gonna replace it with the one from the donor board. I'm gonna reflow VIA 1 just to make sure I have all the connections good there, since I'm not sure if I did that quite correctly. And then what I'm going to try to do is build up the little adapter for this zip package video chip to replace the damaged one. And then at least we'll have potentially a working system, although in all likelihood right now, the Mathco processor is probably damaged, as are the SCSI controller and the floppy drive controller, which I think are these two chips right here. That's the one I already swapped out. That's the serial controller, but these two are probably bad as well. So yeah, basically at this point, almost everything that could have been damaged did get damaged, except for the ROM sim. That seems to be the only thing that actually survived. And I know that because I tested this on another machine and it was fine. So, okay, I know what to do. Here we go. All right, so the VIA is swapped out. I didn't do the SCSI chip, but I did reflow the joints on VIA 1 up here, which I already changed previously. I also double checked that the connections from VIA 1 to the ADB chip are good, and they are. I'm going from the pins on the body of the chip to the pins on the body of the chip, checking for any broken traces. So that's 4 wires. Now there are additional signals that go to this chip, like a clock signal and reset and stuff like that. So it's probably a good idea to check those if we still don't have a working mouse pointer. I still have 4 meg memory modules in here, so this should turn on and work, but we should be able to switch back to these 256 kilobit modules, and then this thing should now be functional. I also have not touched the video memory, so we're gonna have messed up video memory. So let's see what happens when we turn this on. Okay. Aha. It's not working. I think if I plug the speaker in, we'd hear a SAD Mac tone. So I made it worse. I forgot. There's a short on the, I think it's on the new VIA chip. Yep, okay, forgot about that. I was double checking for shorts and connectivity on the new chip I just soldered, and yeah, there was a short. So let me go find that and clear that. I'm sure that's why the system's not working. Yep, there's the short right there. Notice this looks a lot better, the soldering, than this mess over here. So I'm getting better. I'm getting much better at this type of soldering. Okay, so the way I found to clear this is to first glob a bunch of solder into the spot there and then use some wick. And that did the trick. So you can see there's a bit of flux residue, but that short is gone. All right, let's see if it works now. Okay, good. We're back to working again. And I think we're in no better shape. And there we are back where we were before. Let's plug in the mouse. Hey, the mouse works. Okay, so that definitely confirms that I had a bad solder joint on via 1, that reflowing it when I was doing via 2 did the trick. So we have operational ADB. Yes. So now what we got to do is I got to get these 4 meg modules out of this thing. And then we have to get the 256 kilobit ones in and see if we now have operational memory down below this 16 megabytes of RAM in bank 0. Well, actually, you know what we can do? We can install 4 megs of RAM into here because we know that would not have worked before either. So let's get this in here and see if we have now a working system with 4 megs of RAM. Okay, let's see if it powers up. All right, we got the tone, got the gray screen. Oh, there we go. There's the mouse. Okay, good. So, yeah, I mean, I'm not going to call this board fixed because clearly it's got more issues, but we're in much better shape than we were before. Okay, so this is via 2 that I just swapped out. So I'm just going to draw an X on this since that was definitely damaged. This was via 1 here, which I don't really know if it was damaged, but I mean, honestly, if via 2 was damaged, clearly via 1 would have been bad as well. So this is my little bag of parts here with the other bad chips that have so far died in this machine. So we'll throw those in there. And now that really leaves us the integrated WAS machine and the SCSI controller. And I have those 2 chips sitting right here. I took them off the donor board already, so they're ready to go and be reinstalled onto this board. But really, before I go ahead and change these, I probably need to do the right thing and just check to make sure that these are being selected and, you know, we're getting the signals going to those, because the last motherboard that had the bad SCSI, it was just a bad trace, and we know lots of bad traces can happen in that area. Oh, incidentally, when I had via 2 off, I inspected very closely with the loop here just to make sure that there were no bad connections underneath there, and I double checked every single pad and they were all totally fine. And wait, look at this. We actually have an X'd out disk. So that really screams that the integrated WAS machine is bad, because it's almost like it's trying to boot a disk that doesn't exist. Let's plug in a floppy drive and the blue SCSI and pop in system 7.1, and let's just see if this thing can possibly try to boot anything. I'm extremely skeptical that any kind of booting is going to work here, because those 2 chips are, yeah, almost certainly killed. And while we wait here, I have to say, I am so happy I had that donor Mac 2CX board. And it kind of goes to show you that you should really always save it. Whoa. Okay, it ejected the disk. I didn't even think the eject gear was good on this, but it is. Let's see what happens now. Okay, well, yep. I think I'm going to violate my rule, and I'm not even going to try to look for bad traces here. I think I'm just going to swap those chips, because at this rate, we could just pretty much assume that everything is bad on here. And as I was just saying, I'm so glad I had that Mac 2CX board, and it just goes to show that you shouldn't just throw away boards that look like they're super damaged, like they had all the corrosion and whatever on there, because all those chips are coming off that board, and they're allowing me to get this board working again. And in fact, out in the garage, I have this tote just filled with old circuit boards, lots of PC motherboards and things like that. And I often go there to steal parts off of those, especially things like connectors and stuff like that, because those are always almost in good condition. And I don't always have things like the floppy drive connector here. So if this were rusty, I'd just steal it off another board. And there we go, we'd be up and running. Okay, well, it's time to reapply the strips of aluminum foil here and remove these 2 chips. And I already have the other 2 to go back on there, so I'll just do the same thing. Clean up after removal, and then inspect with the loop for any bad connections, and then put the solder paste on there and reattach the 2 chips. And maybe then we'll have a nearly working motherboard, except for the video RAM chip. All right, the SCSI controller and the SWIM have been swapped over. I validated that every single pin is connected to the pad, and I also checked for shorts. Yeah, there were a bunch of shorts, but I cleared them all. See that little bit of white crust that's right there? Don't worry, that's not actually leftover solder paste. That's just some of the flux residue that I cleaned off a little bit with some IPA, but yeah, you really have to get at that to get that all off of there. But that's not actually create a short or anything like that. All right, place your bets. Is this system actually going to boot an OS now? Obviously, we have a bad video RAM chip, But judging by the fact that, well, everything has been bad so far and I haven't changed out the math coprocessor, if we're able to boot into the OS, I am assuming the coprocessor will not be working. Maybe that'll keep the OS from booting. I don't know. Here we go. Let's see what happens. That was weird. It took a little bit longer there before we got a chime. I'm not sure if that's normal or not. We do have a working mouse pointer still, so we're not worse off than we were. We have a booting system. All right. I think the floppy drive's not working though. Oh no, there's no disk in the drive. That is why. Let's put this disk in here. See if this even... It's working. It's freaking working. There is the System Tools disk. Interesting. I guess when you move the window around, it's degrading. It obviously copies the video memory to do the window move. It doesn't redraw the window from scratch. And well, since the video memory is messed up, it's just getting worse. It's getting worse and worse. All right, but the disk drive worked. It booted up off SCSI. Let's see what it says here. 4 megabytes of RAM, which is correct. This thing is freaking working. Question is, if we run speedometer here, I got to run the old version because we're on System 6. Will it even see the math coprocessor? I'm assuming no, but let's see what it says here. Well, it shows the FPU. Let's do a benchmark here and see if it can actually pass the... Oh no, system error. System error number 11. My assumption is that is it trying to talk to the FPU. And the FPU obviously works to some extent. It's just probably damaged on data line 31 there. Okay, so I just rebooted the system. What else could we do to potentially check the math coprocessor? I don't know. Let's play a game. Let's see if a game can work. How about Crystal Quest? I love this game. Let's see what this does here. That's complaining about color. That's normal. Oh, it crashed as well. Somewhere there is a chart you can look up what the system errors relate to. I have a feeling that it probably just has to do with the math coprocessor because that's the last thing we haven't touched on this thing. And it's probably just bad. What I'm curious is if I push the programmer button, unserviceable interrupt. Right, okay. Let's restart the computer. And I pushed the interrupt button so it went into the diagnostic mode. So let's run some of these tests here. So this is size memory. Oh, I didn't clear the code first. Okay. Oops, there we go. Try this again and we'll do response. And yep, 4 megabytes of memory, which is correct. It boots the OS, so we kind of know it works. And the final thing I'm going to do for completeness is I'm going to test the video RAM for the SE30 just to show you that it's going to identify exactly which bit is not working. So we just paste this in. And we get some patterns there on the screen, and there's our response code. Now, notice it repeats over and over again. But that's specifically because the video memory on the SE30 is only 8 bits wide. So all we really need to do is just look at one of these bytes, and then go to a calculator, put it in, and look at the binary representation, and this is telling us right here that bit 7 is the problem specifically. So least significant bits over here, 0, and all the way through 7. And if we go to the schematics and you look for video bit 7 right here, there it is. That is on this chip here, UC6, which of course we know bit 7 here corresponds to data bit 31, which is the damaged bit from the 12-volt line. So yeah, UC6, we already knew which chip it was that was damaged, but just in case you're trying to figure it out, running this diagnostic, that's how you do it. All right, since the system is actually booting, all that's really left to do now is I need to wire up this video RAM chip here to replace the bad one, right? So that should fix that problem. And then I think what I'm going to do is I'm going to just remove the math coprocessor from this board entirely. I want to see if the SE30 works fine without the math coprocessor, which I'm assuming it will work perfectly without it. And if that fixes our system error number 11, that confirms that this is damaged. And then I just need to get another one on the board to restore this back to, complete SE30 performance. All right, we're ready for some testing. I have the math coprocessor removed, which I have to say was way more difficult than these smaller ICs. The larger it is, the more heat you have to do, but I managed to get it off without any damage to any of the plastic stuff around it. And then I also built the little zip adapter here. It's quite a mess, but I think it should work. And I have it in some pin strips there in the socket itself. That means I can easily remove this and just put another chip in when I get one. But you know what, if this works, it's gonna be just fine. To help with my creation of the adapter, I made this little matrix here, which has the dip IC pins here, and then there are same functions on the zip. And then in the middle here, I'm basically saying like this pin here goes to pin 19 on the socket, and so on and so forth. So it's my hope that the video RAM is now gonna be fixed on this, and we're gonna boot up into the OS, and then I'll be able to run some software, and it shouldn't detect the floating point unit, and then we shouldn't have that crash anymore. All right, are we ready? 3, 2, 1, go. Ah, no, it's not even posting. Nothing at all is happening. And I'm wondering if my little adapter is the problem here. Let me pull this out. Maybe I have the zip IC reversed. I'm really hoping that I didn't cause some kind of other damage on here that I'm just not aware of, but who knows? Anytime you do rework on a machine, there's always that risk. So here we go, 3, 2, 1. Oh, come on, really? Okay, I removed this PAL and I put some Deoxit in that socket since that was right by the hot air. Let's see if that makes a difference. All right, yes, okay, good. We're getting a chime now, so now I have to put this video RAM chip back in that I made. All right, so is this little contraption gonna work? We won't see those vertical bars. If it does, 3, 2, 1. Oh no, oh wait, oh yeah, of course. So the funny thing is, the original pattern looked all weird now, but that's because I have two different brands of chips now. We have a Hitachi chip in this socket, and we have an NEC chip in the other. So that means that the default power on state is gonna look completely different. So I have all the peripherals reconnected to the outside. Let's turn that on. Oh no! Now we're getting a crash again. What's the problem? Oh boy, that's interesting. All right, fresh Deoxit in all of the PAL chips there. There's that weird pattern again. Let's see if this can actually get through the RAM diagnostics. Got a mouse pointer, so that's a good sign. Now, one of the PAL chips is actually used for clock generation and some other timing stuff on the motherboard. So I think if there was a bad connection there, that possibly could lead to issues. Yep, there we go, we're booting up. Oh no, clearly it's not happy. Oh dear. Let's reboot here. Now what I really don't know is that it's quite possible that the system is looking for the math coprocessor, and the fact that it's not even there on the SE30 might make it very unhappy. All Macintosh 2 machines have a math coprocessor up until the Mac 2 SI, and the Mac 2 SI specifically, it was optional. And it actually has me wondering that if the system sees that this is a Mac SE30, it's just going to try to use the math coprocessor at boot, and well, that's not working. So I'm going to put the System 7.1 disk in the floppy drive, and let's see if this thing can boot from the disk, and maybe there's some kind of a difference with the System 7.1 versus System 6.07, which is what's on the Blue SCSI right now. Okay, we're having some weird issues here where the screen is flickering, but the computer's not crashing. Ah, you know what's weird? I think there's a problem with this connection here for the power. Because it seems to be extra sensitive if I touch the wire. Let's see what happens. This could entirely be a power problem right now, and there might be corrosion inside that connector there, since it's right near all the capacitors that leaked. Yeah, look how it's actually booting now off the disk without that flashing anymore. All right, well, the System 7.1 is telling us it's got a bad F-line instruction to temporarily turn off its engines, restart, and hold down shift. Well, I don't think it's that. I think there's something else going on. Okay, so all I have right now to go on is System 7.1 when it boots up and it says bad F-line. And I'm pretty sure that has to do with the floating point unit. And the fact that it's not on the board is leading me to believe that I'm just gonna have to reinstall the chip. I was hoping to finish this video off, because it's already super long, without the chip installed, just to show, hey, it works without it. Well, it seems like the SE30 doesn't work without it. Well, I hope that's what's going on right here. So I'm gonna go and attempt to reinstall this onto the board. It's gonna be difficult because getting it off was really hard. And then hopefully this fixes the problem and this motherboard is finally fixed. All right, we're back. And that was extremely unpleasant. Things were going really well and I was reattaching that chip, and then I accidentally bumped it when all the solder was molten, and then it right away was recongealing and the chip was out of alignment and I had to remove it and start again. The math coprocessor from the donor board though is attached, and I've gone through and checked for continuity on every single pin and also checked for any shorts. Do be aware if you're reattaching one of these that there are several pins, and I forgot which one they are. They are all actually joined together, and I checked on another motherboard just to make sure that it's the same way. So that might give you a false reading if you're checking for shorts. All right, we're ready for testing. So at this point, everything that was on data line 31 that got shorted to 12 volts right here has been replaced, both via floppy controller, SCSI controller, serial controller, sound chip, and then of course the video RAM chip here, the math coprocessor, the CPU, the ROM, and well, I'm using different RAM, and the only thing that's original is the ROM sim. And anytime you do any rework on a board, there's a risk that it could be damaged from that rework. So honestly, every time I do this stuff, I have to keep my fingers crossed here that it's gonna work. So here it is, the moment of truth. 3, 2, 1. Okay, we're getting the good power up. That's the new pattern that this machine does due to the hybrid nature. And is it going to work? Please, please work. I don't want that flashing. Okay, here we go. Come on. Yes, yes. Okay. Wow. Wow, wow, wow. Okay, well, now we know on an SE30, you cannot boot at least system 6.08 or 7 or whatever this is, or system 7.1, which is what's on this disk here, without the math coprocessor installed. It is very unhappy about that. There we go, we have 4 megs of RAM. Now, we were trying to run speedometer last time, 3.06, and it ran, but then it crashed. And my hypothesis was it was the bad FPU or the damaged FPU that was causing that to happen. Okay, we're seeing the FPU. Let's try to run a performance benchmark, and this is where it crashed. Oh yeah, it's working. It was already crashed by now. Wow, so this thing is finally working 100%. Unfreaking believable. And there we go, we're done. 3.958 is exactly what we should be getting on this version of speedometer. Let's try Crystal Quest because that was crashing as well. Now you might have noticed when the system booted up that I had the Lemmings window open, and that's because Lemmings did work without the math coprocessor. So I actually left it running as sort of a stress test just to make sure the system was working properly, and that was before I replaced the video RAM. So of course the screen had those lines in it, but the game was working fine. And there's Crystal Quest, and it freaking works. So it was crashing before, and now we're good to go. Awesome. I really do love this game. As a kid, I played the heck out of this game. Whoa. Well, the board is fixed. I wasn't 100% sure I'd ever really get this thing working, but in the end, I did. Now, there's a big lesson to be learned here, at least for myself, is that when I'm recapping, I'm using parts that have a different footprint than the original caps. If there's any kind of overlapping of traces that are underneath the caps, it's just really important to take the extra time to position the cap in a way where it overlaps the minimum number of traces, especially the exposed ends where the metal is there, and to also inspect very, very carefully for any of the solder mass that's been eaten away by the original leaking caps that are on the board. I've recapped, I don't even know how many machines at this point, and I've never run into this exact problem before. But it's not the first time I've accidentally sent 12 volts into the data bus, and that happened on a TI-99 once, where I accidentally bridged one of the CPU pins to an adjacent trace because there's no solder mask on those PCBs, at least around the pins there, and I accidentally fed 12 volts into one of the data bus lines. But luckily on the TI, it was on a line that didn't go to every other peripheral on the board. I think it damaged maybe one of the SRAM chips and just the CPU, and then the rest of the machine was fine. Kind of unlucky on the Mac SE30 design though, where data line 31 just happens to run literally right where the 12 volts is, and that data line along with its 7 other cousins goes to every peripheral on the entire machine. If it was one of those first 24 data lines on the other hand, then just the CPU and the math coprocessor would have been damaged, and maybe the RAM and maybe the ROM here. But all the other chips, they would have survived. So let this be a cautionary tale if you're doing any recapping, especially on the SE30. Now, I do have to say that this damage that occurred to this board led me to discovering and figuring out how the diagnostic mode works on all these Macintoshes. And if it wasn't for the failure on this motherboard that I caused, then I would have never gone down that path. And I'm really hoping that the new information I've shown on how to do diagnostics on these machines goes a long way to helping other people get their non-working Macintoshes working again. I also want to point out that in part 1 I mentioned with this motherboard repair that I didn't want to just go replacing every single chip and hoping that it would fix the machine. The irony there with that statement is it would have actually fixed this machine if I had just swapped out every single chip that was on data line 31. But we all know that's not how I like to work, and I like to understand exactly why a machine has failed first before I go and do all that stuff. So in the process of figuring that out, we figured out how to use the diagnostic mode, and then that also led me down the path of understanding how the RAM size function works on the SE30 as well, which is something I completely didn't know. And then using critical thinking skills, we were able to see the machine boot with 16 megs of RAM in here that kind of proved that VIA 2 was actually the problem. And then I kind of gave up and just started replacing all the rest of the chips, because once I had seen a few damaged chips, we kind of knew for sure that the rest were probably done as well. Oh, and then we figured out as well, you cannot run a Mac SE30 without the Mathco processor installed. So if you have a faulty Mathco processor or an eat and trace around there, then you're going to get that kind of crashing and those types of errors that we were seeing with this machine as well. So with all that said, that is it from a Macintosh SE30 repair series. This motherboard is fully operational, the last motherboard is fully operational, and I think I've discovered all there is to really discover right now about repairing these machines. So I'm going to put these motherboards back into their respective shells, and I guess I finally get to move on to something else here on the channel. So I hope you've enjoyed this repair series, and I hope that you've learned something about repairing these 32-bit machines. I've certainly learned how to do SMD soldering on PLC sockets. That's something I'd never really done before. And well, now I've done all these chips here, I've gotten a whole lot better at that. So thanks to everyone who gave me tips on how to do that stuff. If you've enjoyed this series, I'd appreciate a thumbs up. But if you didn't, you know what to do. Huge thanks to my supporters that make it possible I do this full time. Supporters get to watch my videos a week earlier. So that means in a multi-part series like this, when part 1 came out, they're already watching part 2, which can be kind of cool for some people. So anyways, thanks to them. You can become a supporter. There's a link in the description below. There's YouTube memberships as well, plus Patreon. Both are available. Hit subscribe if you haven't already. It really helps me out. And I think that is going to be that. So stay healthy, stay safe, and I'll see you next time. Bye.